a black screen.
We also see a black screen.
That's great, but not intentional. Let me. Okay, that's a great start. Okay. Sorry, do you see it now?
Yes, it's good.
Okay, great. Yeah, so hi everyone, good morning. Thanks for the invitation. As Via mentioned, I'm a postdoc here at the center, and I'm extremely excited to present this latest work about optimal control of quantum thermal machines using machine learning. And basically everything that I'm about to tell you is summarized in this preprint. And I must also mention that this is a joint collaboration with Juan Carrasquilla from the Vector Institute. Yeah, anyway, let's begin. So I want to start by saying something that, I mean, most of you know very well, is that many problems, if not most problems in physics, are essentially optimization problems. So, for example, in classical mechanics, we have the Ballista-Horn problem, for which we want to find, we construct a Lagrangian, and we want to find the minimal action. And I could easily spark a debate, a loud debate, of saying whether we really care about the integral solution to that motion, or can we just have some other representation to that? So that's one example. The other one is given here in this cartoon. It's a cartoon of PEP's tensor network. So those are used to approximate or to represent quantum ground states of quantum Hamiltonians. Another recent example is this VQE, the variational quantum eigensolver, which is again used. It's a variational ansatz to approximate ground states of again quantum Hamiltonian in quantum computing aspects. I forgot to say, please interrupt me with questions. Otherwise, it will be. It's. I mean, I'm sure most of you know that it's hard to speak. Give a seminar via Zoom anyway. So please interrupt me with questions. So next on my list of topics, we've covered optimization. Now, machine learning. So machine learning had a lot of successful applications, and those include image recognition, natural language processing, things in chemistry, in biology, finance, healthcare, everywhere. It affected everyone. In recent years, it has also impacted physics. So specifically, a few examples, and those are you can read a lot more in this beautiful review by Juan. But it was used in phase classifications, in quantum state representations with neural networks, such as the example of a recurrent neural network that I'm giving here as a cartoon. Time evolution, so dynamics were studied, and so on and so forth. And I do encourage people that are interested. There's this very nice review. Moving forward, why machine learning is so successful? Well, it's essentially why neural nets are so powerful. So these are highly expressive set of ansatzi. They're very generic. It could be model free, and as I'll show you today with just one example, they allow for an unbiased discovery of various quantities. And in recent years, I think a lot of success is owed to the fact that training those or optimizing those neural networks became extremely easier by using automatic differentiation or differential programming, which I'll tell you about in a second. But basically what it tells us that now we have however convoluted functions, and these are, again, very complex functions, as I'll tell you, but now we have access to exact gradients. So we can train those, we can optimize those to perform a specific task very, very easily. Right. So for most of us outside the field of machine learning, when we hear the word gradients or derivatives, we immediately think about finite differences. And I want to start discouraging you to use that. So here's a simple example of a not so smooth function. And suppose that we have, so the function is mostly smooth, but there are some regions where it's not. And suppose we want to sample its derivative. So we know that the answer highly depends on the mesh we choose. For example, here, in this mesh that I've chosen here, you would say the derivative is the derivative is 0 everywhere. But obviously that's not the right answer. And this is one example for where the mesh is important, both for the value, and so it's important to get the correct value. But it's also important when we think about a huge process, so a huge numeric and a very involved numeric calculation for which we want to find the derivative with respect to some quantity. So we know that finite differences would be a bad solution. So there is an alternative, and this is what I want to tell you about. It's called backpropagation. So basically, whenever we want to compute, so this is an algorithm to compute exact gradients, and what it means is that it basically tells us that we need to use the chain rule. So, for example, if we have a function which is a function of g of x, so we have f, which is a function of g of x, and we want to compute its derivative with respect to x, then what would we do? We would basically first compute g of x, then compute the derivative of f at g of x and multiply that by the derivative of g of x, right? So the same way we can think about, in the same way we can also use that to compute gradients of very convoluted functions, specifically neural networks. So what is this neural network? So it's basically a set of composite functions and matrix multiplications. And the way to think about this is that each layer has some inputs, and the inputs are the previous layer's outputs, and also some set of weights. So and at each layer we act with some nonlinear functions, but at the end of the day we have input which comes from the previous layer and a set of weights. So backpropagation tells us that we go to the end and we compute the partial derivative with respect to each of these weights. So basically, we apply the chain rule many times, propagating backwards. So this is exactly the opposite of what we would do when we actually calculate what is the value, because when we calculate what is the value for some given input, we propagate forward. Here we would propagate backward, keeping in mind that we had all the previous derivatives. And this is a way for us to basically optimize, because we find the gradient of the output, which could be some sort of a cost function with respect to each of these weights. So that was my take on trying to explain how these things work. But in practice, what is done is that at each algebraic quantity that we write, each algebraic calculation, for each line of code, basically, we need to specify, or I should say it's already specified, what is the gradient of that function. So for example, if we have...
So may I ask a question?
Just one last sentence. So if we have a sine, if we want to compute a sine at some point, we also keep in mind that the derivative is a cosine. So we keep at each point, at each step, we keep both quantities. Please, Italo. So
would you say then that machine learning and neural network approach replaces the numerical analysis wisdom?
Sorry, approach what? Sorry?
The neural network approach that you describe, does it replace or complement the numerical analysis wisdom?
Sorry, what's the last word? Wisdom?
Yes, numerical analysis is a very established long-term thing that in Tel Aviv University, Professor Schenheim told me 100 years ago.
So so to some extent, what I think, and this is, let me answer this differently, perhaps. I don't think it replaces, but think of, this is why I gave this example. So we all know how to solve this, right? Well, at least we all know how to get to the equations of motions. Can I assume that, right? But at the end of the day, you would get a complicated integral equation, which you may have to, in order to get some properties of it, you may have to numerically compute that, right? So I can offer you an alternative way, giving you a very powerful ansatz, such as the one that is depicted here, and it would solve that problem. So you would be able to get, at every instance of time, you would be able to get the entire information about the motion of the barista. So it's not a way, I wouldn't say it replaces, I would say it's a complementary method.
I use that word too.
Sorry?
I use that word in the question too.
Okay.
Replacing or complementing.
Yeah, so I would say it's complementing. And I'll show you, so next I'll show you an example where, things become very, very complicated, and we just use a very expressive ansatz, and we get a solution, and it's I would say it's great for us.
Okay, thank you.
Thank you. Right. So so I try to explain this. It's probably less complicated than the way I presented it, but if you have any questions, please let me know. So the story I'm about to tell you today is about optimization in a completely different field. It's in the field of finite time thermodynamics. So I'm gonna take a very old problem, and I'm gonna use basically machine learning or deep learning to investigate that, to optimize that. And I also, as a bonus, I'll show you that we discovered a flawed thermodynamic definition using this method, and we actually corrected it. So I'm going to present the what we think is correct, and at the end I'll show you what was not correct. Okay. So a bit of introduction to thermodynamics. So here's a picture of sorry, not a picture. Sorry, it is a picture of a diesel engine made more than 100 years ago, and that was one prime example of an engine. But nowadays these are contemporary engines. So we think of nanoscale, basically molecules that act as engines or as quantum thermal devices. So optimizing their performance is a huge problem in quantum thermodynamics. And actually, in thermodynamics in general, you'll notice that we're bound by Carnot bounds, which tells us that, for example, an engine could reach its maximal efficiency. However, that would happen for a very, very, very slow process, during which so we have high efficiency, we obtain the maximal efficiency, but the extracted power is actually 0. And this maximal efficiency doesn't care about anything but two numbers, the two temperatures, the two cold and hot reservoirs that were coupled. So this is the efficiency for the refrigerator. I'll remind you this a bit later. So this is, again, very slow quasi-static processes in thermodynamics. However, real thermal devices operate in finite time cycles, meaning that now this is in the domain of finite time thermodynamics, as I said, and basically now we could ask the question: how does the efficiency decreases when we have these heat to work conversion processes that take place in finite time cycles? So basically, what I said is that we could think of a natural figure of merit, which is denoted here by chi, which is the efficiency times the power output. So as I'll describe next, I'll be talking about refrigerators. So the power output is actually the cooling power. This is it's proportional to the cycle's duration. So as I said before, when we have a very, very long cycle, the power drops to 0 as 1 over the cycle duration. And as I said, there's the efficiency, for these long cycles, the efficiency actually increases. So one increases, the other one decreases. In other words, that's our problem, that both these quantities actually compete. So the question we'd like to ask is, can we design an optimal finite time process given that this is our figure of merit, the efficiency times the power output? Any questions so far? Okay. So let me describe the specific example we were studying. So the Otto engine or refrigerator is a 4-stroke machine, and it can either operate as an engine where we have heat to work conversion, or as a refrigerator where we input work and we extract heat. So the working fluid in this example is an harmonic oscillator, a time-dependent harmonic oscillator, and we have some 5 external parameters, which are the cold bath temperature, 1 over beta 1, the hot bath temperature, 1 over beta 2. We have the initial frequency and the final frequency, and we have the cycle duration. So those are sort of our external parameters. And the question we would like to ask again is, how do we optimize this cycle, but for given parameters? So we don't want to change any of the external parameters, but we want to change the variation in time, or how do we go from this frequency omega 1 to this frequency omega 2? And what I exactly mean by that, I'll tell you next when I describe the strokes of this engine or of this refrigerator. So we start at point
Sorry,
A.
before you continue.
Yeah.
You were saying that you're going to change some definition of thermodynamics.
Yeah.
Have you done that already, or you will do it?
I will do it. So I'll give you.
Thank you.
I'll give you a hint soon about this.
Okay, cool.
Yeah. So I want to describe how this machine, this refrigerator operates. So bear with me for a second. We start at point A, and we have an harmonic oscillator with frequency omega 1. And during a duration of tau, we go to we basically compress and we go to a frequency omega 2. So omega 2 is larger than omega 1, therefore we compress. And that happens, as I said, during a duration of tau. Next, what happens is that we thermalize with the hot bath. So here, the frequency is fixed, and we thermalize with this bath, and some heat is extracted to this hot bath. So this is this quantity Q2. And we assume this to be an instantaneous process. Unlike the previous one, which took us some time tau, we assume this to be instantaneous. This is not an important, so obviously it's not a sort of a real assumption, but it's not important to what I'll tell you next. And you can ask me about it later. So yeah, next we're at point C, and now we expand, which means that we start at frequency omega 2, and during a duration and during a time interval of tau, we decrease the frequency back to omega 1. Lastly, we thermalize with a cold bath given a fixed frequency omega 1. And now heat is, so this quantity Q4, heat is extracted from the cold bath. So when heat is extracted from the cold bath, this is exactly the refrigeration, because we make the cold bath essentially even colder. And again, we're assuming that this happens, this is an instantaneous process. Okay, so as I said, this quantity tells us by how much heat quanta we remove from the cold bath. Hence, when this is positive, this is our refrigeration condition. This means that our refrigerator actually works as a refrigerator. And Itamar, to answer your previous question, when we're thinking about efficiency, we need to know what is the energetic cost of our cycle. So there are basically 4 contributions to that, coming from the expansion and compression. So in the expansion and same for the compression, we have W1. W1 is basically the average energy difference between the final and the initial states. So basically it tells us how much work we've put, so how much work we've put into the system just with final minus initial average energies. And there is also the actual cost of the driving, which is denoted here by CAB and CCD. This is basically to answer the question, so we varied some Hamiltonian with time, how much energy did that consume? So I'll give you a hint. So this law definition that was there before us had to do with these 2 quantities. And we corrected it. And I'll tell you about it a bit later. Right. So again, I said we don't alter any of the external parameters. So basically what we want to ask is, what is the optimal driving between omega 1 and omega 2 given by this function omega of t? Any questions so far? Okay, so I need to give you a bit more information. This is going to be a bit technical, so bear with me, please. So there's a notion, so we said we have a time-dependent Hamiltonian, and now the question is, how do we drive it to get from omega 1 to omega 2? Now, our goal basically is to speed up the expansion and compression strokes, but we want to mimic an adiabatic time evolution. So what do I mean by that? So if I take this Hamiltonian and I were to evolve it according to the adiabatic approximation, meaning that I would have evolved it from omega 1 to omega 2, but very, very, very slowly, I get some state at the end. And what I want to do is I want to get to that same state, but using a finite time time evolution. So how does that work? So one way to achieve this, that's called counter-adiabatic or transitionless driving. It basically tells us that so again, in the adiabatic theorem, we know that if we drive things slow enough, there won't be any transitions. So what we want to do is we want to suppress, now if we want to follow the same procedure, but in a finite time, we want to suppress all these excitations. So the way to suppress these excitations is basically to add a term to the Hamiltonian. So that was our original H naught. It was our time-dependent harmonic oscillator. Now we add terms which we denote them here by HSTA, and CD stands for counter-adiabatic. We add the terms that basically are responsible to these transitions. So we suppress the transitions. And you can see that for an harmonic oscillator, these terms, so they depend on the driving frequency and its derivative, but mostly we get a potential, we get a highly non-local potential because now it involves both X and P. So we can still diagonalize this and get to a new harmonic oscillator, which with modified frequencies. But basically, sort of experimentally, the problem is that we would have to have a non-local potential. So both time-dependent and non-local potentials. So in order to overcome this, we can act with some unitary on this previous Hamiltonian that I showed, and this is this unitary. And what we get at the end is we get a local. So look here, please. We get a local potential, so we get a local potential with modified time-dependent frequency. So we still get an harmonic oscillator, but its time dependence now is given by this function, which now involves both the first derivative and also the second derivative. But it comes with a set of hard constraints because, again, remember, we want to end up, so we start with some initial state and we want to end up with a specific final state. So these are the conditions that this driving must meet in order to get to the same final state as we would have gotten from an adiabatic time evolution of the original Hamiltonian. So just to recap, the price we pay is that we modify the driving frequency, but it also comes with a set of constraints. Any questions so far? Okay. So that was one way for shortcut to adiabaticity. I'll take a quick break to tell you about different approaches or a different approach, and this is a work that has been recently done in Ephraim Steinberg group. So they were interested in cooling a quantum gas. So this is its distribution at the beginning, and this is its distribution at the end. And since you can see that it's quite narrower in the, so this is momentum and this is position. Therefore, we understand that the gas has been cooled, and they achieved that with a different technique than what I told you about so far. They achieved that with what's called delta kick cooling. So basically, you see this is the time dependent potential. You can see the red one here. This is the time dependent harmonic potential frequency, the driving frequency. So you can see that there's a kick, there's a delta kick at the beginning. Then there's something practically constant, but there's a delta kick at the end. And the reason why there's a delta kick in the end is exactly the same one as we have with these constraints, is that we want to remove all additional phases that we've accumulated during this time evolution. So these kind of approaches, there is a name for those. Those are sort of these bang approaches. Okay. So back to our problem, we have this shortcut to adiabaticity, this STA driving, and there's there's a sort of a naive solution to that. We can think of a polynomial, and given this kind of a polynomial, it immediately satisfies these three initial conditions, and we're basically left with three boundary conditions at basically what happens at time tau. So a naive solution would be to have three coefficients of this polynomial, and this is what is widely used in the literature, and we use that to benchmark our results. Okay, so there's a polynomial ansatz that satisfies these constraints, and we're going to use this as a benchmark. So I told you about the figure of merit, which was the efficiency times the cooling power. Specifically for us, the efficiency is given by the heat extracted divided by the energetic cost, which I told you about. So the amount of energy we extract is basically set by the external parameters. So there's no, again, since we're not changing any of these external parameters, there's no optimization that happens at this level. The only and similarly for those quantities, those were the associated work that I told you about. They're basically sort of the same expressions for that. So these quantities only depend on these external parameters. So what can we actually optimize is we can optimize over the energetic cost. So this, as you can see here, depends on the driving. It's an integral equation that involves the first and second derivative of our driving frequency. And this is the quantity this is part of the quantity that we optimize. I'm saying part because this does not take care of these 6 constraints that I mentioned earlier. Okay, so what do we actually do? So we take a deep neural network, and that represents our time-dependent driving frequency, omega tau. So we took a very expressive ansatz, very complicated ansatz, and that we have a single input, which is time, and the output is omega t. It's pretty much standard, but the fact that we added a small polynomial layer to remind us basically what I showed a couple of slides ago, and this was done solely for sort of faster convergence. Everything works fine without this layer. So this is just as a side remark. So what do we actually do? So we use, as I told you before, we use differential programming, which allows us to calculate exact gradients of however convoluted function. In this case, our convoluted function is this neural network. But moreover, it's not just this neural network. It's the fact that we have to integrate over the first and second derivative of that function. And this is done very, very easily using differential programming. And for this optimization process, we play a game, and this game is better known as reinforcement learning. And what does that mean? So again, we start here. We have our neural network ansatz, which basically tells us the shape of this function omega t. We feed that into our thermal machine. So basically, what we do is we calculate the energetic cost of that driving, and then from that we derive what is the efficiency and so on and so forth. And we feed that to a reward-based optimizer. So that reward-based optimizer, I'll show you the essence of that in a second. But basically, it takes into account our figure of merit, which was the efficiency times power output. But also it takes into account these constraints that I was telling you about. And our goal is to minimize those. So how do we optimize those? We use those gradients, which I told you about, and we can feed a new guess to the thermal machine. So I'm describing sort of an iterative process that takes place. Right. So how do we calculate the reward? Very quickly, we have the energetic cost function, which I showed you before, and we penalize for breaking the constraints. So yeah. So now let me show you the results. So in gray over here, so this panel shows you the driving as a function of time. The gray was the polynomial ansatz, and these colored ones are the neural networks optimized results. Here I'm showing what the actual driving looks like. So what do I mean by actual driving? Remember that we went to this, we took the original Hamiltonian, we added some terms to it, we got a new potential, which was local. So this is how these functions actually look as a function of time. So this is the actual driving that you would pursue in the lab. Moreover, here you can see the first and second derivative with respect to time of these functions. And you can see that for the most part, they kind of follow each other. And the reason they follow each other is because our cost function made them do it, because the energetic cost basically involves the first and second derivative, and they come with opposite signs. So in order to minimize this guy, these two functions sort of need to follow each other. So what do we actually get? So here I'm plotting the efficiency, here I'm plotting the figure of merit, which was again the efficiency times the power output. And you can see that we benchmark it with two things. These are the neural networks results. And this is as a function of cycle time. So these are the neural network results. And you can see that this was our benchmark. We beat it by, say, 50%. And we also benchmark it against what would happen if we just quench the system really, really hard. So we just switch quickly between omega-1 and omega-2. So obviously at long times, there is a huge advantage of doing either of these approaches over this. When we just look at the efficiency, so again, this is what we optimize for. And now we can turn and look at what is the efficiency doing. So the efficiency is doing, so again, the neural network's efficiency is doing better than the polynomial and much better than this sudden quench stuff. And you can see that at long times, we approach the adiabatic efficiency value. So when we approach the adiabatic efficiency value is also when you see that the two things, both the polynomial, both the neural network, kind of give the same figure of merit. So, and this is expected at long times, we should approach the adiabatic. This is the instantaneous. Here I'm showing the instantaneous energetic cost of this shortcut to adiabaticity driving as a function of time. So basically, I'm showing this integrand over here, and what you can see. So again, the gray is the polynomial, the colored ones are the neural networks. So in the bulk of this cycle, you can see that we're able to minimize the cost substantially. And this is again to remind you when the first and second derivatives were able to follow each other. However, in the beginning of the cycle and at the end, due to those constraints, this is where all the energetic cost takes place. This is where the two can't behave similarly. Okay. Now I come to the last part of what I wanted to show you, and this is where a previously conceived energetic cost function or a thermodynamic definition actually fails. So what people have used before to calculate the energetic cost of this shortcut to adiabaticity driving is they took the new Hamiltonian, which included the original Hamiltonian plus the additional terms, and subtracted the original Hamiltonian. So basically, they took the cost was basically the mean difference between the two. Hence, it was the mean. Sorry, it was the mean of the additional terms. That's what they took to be the energetic cost. And that's, again, that's very, very intuitive, because you could say, okay, I have my original driving, and now I add something to it. So the cost should be whatever I added. And this is something that our deep learning procedure kind of showed us that that's not the case. So we took those we took some extreme parameters for which we get an unphysical result. And let me tell you what happens. So we tune the parameters to be near the refrigeration zone boundary, which means that our system still acts as a refrigerator. However, when we try to optimize according to this cost function, to this energetic cost function, we get something that is unphysical. We get an efficiency that exceeds Carnot, and that cannot happen. Quite frankly, one can actually, besides an efficiency that exceeds Carnot, we can get also negative efficiencies, and that's obviously not physical. So whenever we get those, we can use our definition, which is based on the, I don't know if you can see my screen. My screen
becomes dark suddenly.
Is it okay now?
Yes.
Okay, thank you. Yeah. So anyway, what I was saying is, whenever this definition kind of failed, for the same driving, if we calculate using the expression that we derived, we get a physical result, which is well below Carnot. And this is, so I just want to say that this point is still under debate. There is no answer to what is the exact form of the shortcut to adiabaticity energetic cost. Let me give you sort of a different explanation. And here I drew an RLC circuit. So we know that the dissipation lies in the resistor, right? So we have a way of saying what was the power dissipated in that resistor. In the equivalent does not, we don't have the equivalent for thermodynamic processes, and the Schmidt norm or the way we calculate this is just a proxy for the energetic cost. We cannot prove that this is the exact energetic cost. But what we could show, and this is what we've shown, that using this method, this deep learning method, we could show that the previous definition was completely wrong. Right. Yeah. So let me conclude. We were able to achieve a twofold decrease of the energetic cost compared to this polynomial ansatz, and overall a 50% increase in the figure of merit. As I just told you, we discovered the flawed thermodynamic definition using this method, and we were able to correct it. We solved a hard constraint problem, so it's optimization plus hard constraints. And this is essentially this way of thinking about things. This way of optimizing is essentially a new paradigm for quantum control problems. So it's just the problem became now defining defining the problem at hand as an optimization problem, which is in physics that's often not very hard to do. On the future side, we could ask the following questions. We could optimize the entire cycle, including the thermalization with the baths. We can think of cycles that do not include the shortcut to adiabaticity, and in those we would not have any cost to the driving. And obviously the expressions would be different than the ones that I showed you, but at least we won't have this cost. So the efficiency may go up. In addition, as I said, we could study this working fluid bath thermalization processes. We can characterize other processes, other devices, given a model, and this is again the strength of such a method. And more on the technical side, I showed you that we are able to optimize with these constraints by inserting those into our cost function and penalizing. However, something that has came up recently is that there are now packages that allow actually constrained optimization. So one doesn't have to kind of include the constraints in the penalty. One would just write some cost function, write the constraints, and hopefully the computer would solve everything by itself. Yeah. So thank you for the attention and the questions.
I have several questions.
Very much. Yeah. So indeed, if there are questions, sorry, I'll just stop the recording. So if people feel more comfortable asking.
Oh, it's okay. You can record me.